um, in in the detective business, we have something called the Fifth Amendment, where you can be silent instead of answering questions which might incriminate. Sounds great. Great. Well, and just briefly, I'm an astronomer at the Washington State University. It's in Pullman, Washington, down stateside, and my specialty you'll hear about. So it's a rare thing that I get to talk about my research. Um, but don't worry, it won't get too technical. So let me set the scene for you here. See if I can flip over to the pictures. And of course, that didn't work the first time. Let's try again. All right, hopefully you can see something prettier than my face. All righty. Well, in that case, I'll set the scene for you. And the scene it was a dark night in a universe that knew how to keep its secrets. But on the ninth floor of the Webster building where I work, one light still burns. So you could hear me, but you couldn't see my screen. We're good? Okay, I'm going to share screen again. There's always a glitch or two. All right, so this the title of this talk is Guy UVOIR Light Detective. That's going to be me, your guide through the universe tonight. My name's Guy Worthey, and I'm a light detective. Tonight's episode is the mystery of galaxy formation. They're up there, those galaxies. We've been taking pictures of them for a century and a half, but what makes them tick? Let's find out. They come in different shapes, as you might know. There's the spirals, there's the lenticulars, there's the ellipticals, there are interacting galaxies, and we also know that galaxies like to gather into groups of galaxies. But you can't smell them, you can't taste them, and you can't touch them. All you get from galaxies is their light. And if all you've got is light, you need a light detective. Aren't aren't you glad you came today? Let me introduce to you an early light detective. His name was Joseph von Fraunhofer. He was a physicist, and one of the things he did was he took some sunlight and he uh, let the sun shine through a crack in the wall, and he put it through a prism. And when you shine light through a prism, it splits up, and one end looks blue to the eye and the other end looks red to the eye, and in the middle you've got all kinds of different colors. And of course this is the rainbow, and to an astrophysicist we call it the spectrum. So if you know about light, which I do because I'm a light detective, you can assign those colors to wavelength numbers. So here are some wavelength numbers where the blue end is around 400 nanometers and the red end is about 700 nanometers. Bluer than blue, that's the ultraviolet. Redder than red, that's the infrared. And one of the remarkable things that Fraunhofer discovered was that there's light out there in the ultraviolet and the infrared. He did this by taking a thermometer and sliding it along the table. And his thermometer got hotter when the light was falling on it. But even when the light couldn't be seen, it still heated up the thermometer. So we've known about those other wavelengths for quite a while. He also had a pretty good prism. And so this is the type of thing you see from the solar spectrum if you have a good spectroscope or prism. On the top, that's sort of what you might see if you're Fraunhofer, and then on the bottom, that's what our computer light detectors would detect for us. So basically a row of numbers, and there's a lot of structure in there, isn't there? There's Fraunhofer's designations are on the top there. So K and H and G and F and E, those are the things he saw. He wrote them down. He said, yeah, these are the prominent dark lines in the spectrum. Mostly it's full of light, the sunlight, but then in certain places, certain wavelengths, it's dark. There's less light at those locations. And let me just highlight one here at D, letter D. That one we now know is due to a pair of sodium lines. So it's one element in the sun that causes that particular dark line in the spectrum. And the one labeled F, that's due to hydrogen. And the one labeled E, that's due to iron. And the lowercase b, that's magnesium. And so forth and so on. All of those little lines are due to one of the 88 known elements, which is pretty nifty. So we know right away the sun has got all those things in it. So the sun has those elements. And today we can make models good enough to figure out that it's got those same elements that the Earth does in about the same proportions within some slop factors due to obvious things like the sun being gas and the Earth being solid. Ground-based telescopes, so down here at Dominion Astrophysical Observatory, for example, DAO can see in the visual window and the radio window. And those are the easiest places from the ground. But for the other wavelengths, you need to put your telescope somewhere else. This figure is the electromagnetic spectrum, and all these names, gamma rays, X-rays, ultraviolet, visual, infrared, microwave, radio, all those names stand for the same thing. Those are all kinds of light. And the only difference between them is the wavelength of the light that's coming toward us from space. So that's quite a lot. We're not going to delve any further into that. But all of that is part of my bailiwick, right? Because I'm a light detective. So we need telescopes. I mean, in the visual, you know kind of what that looks like. In the other wavelengths, you need other sorts of light gathering devices. And so we have the James Webb Space Telescope on top there and the Greenback Radio Telescope. And then in the middle is Hubble Space Telescope, which I will mention in particular. For example, let's look at this Andromeda galaxy. It's called M31. It's the big galaxy in the middle. It's got a couple of companion galaxies. There's M110 and M32. They're small and rounder and less spectacular, but they are also interesting to study. So let's point our telescope, and let's point Hubble Space Telescope in particular, just north of M32. And Hubble Space Telescope, if you are an aficionado, you know it takes a tiny, tiny piece of sky and looks at it very, very sharply. And so if Hubble Space Telescope looks there, what we get is this picture. You can ignore that white stripe through the middle. That's just a gap in the detectors. What else do you see? You see some really, really bright stars. Those are our stars in the Milky Way. And then you see speckly stuff. Those speckles, each one of those is a star detected individually in M32 or M31. Let's do one more zoom in here. Maybe you can see them a little better. The really bright ones, those are foreground of the Milky Way, and then everything else are just thousands of stars in our neighboring galaxies out there. Well, that's a clue right away. So those other galaxies we want to know about, they're composed of stars. What we see is starlight, but the galaxies are just so far away, we can't see the stars one by one, except for this nearby example with a very special telescope. So what we do see is the smeared, sort of combined starlight from all those galaxies out there. But they're stars. They should be similar to the stars we know about. And we know about local stars. We know about also star clusters. We have two types of star clusters nearby. So let's start there with a little background on what do we expect from stars. And maybe we can use these stars to find out about the galaxies. So locally, we have two kinds of star clusters. We've got globular ones that are very spherical and round and dense. So you look at these things and they tend to have hundreds of thousands to even maybe 500,000 stars in them. And they're quite interesting because all those stars formed at about the same time out of the same cloud material. And yet they've survived for a long time because almost every globular cluster is really old, as in over 10 billion years old. There's not very many in the Milky Way, though. There's only 150 or so. Open clusters are much more common. There's thousands of them in the Milky Way. They are looser. They are more spread out. They're generally lower mass, and they tend to be common, but they also tend to be young. And so we think these don't usually survive forever. They eventually evaporate. They eventually fall apart. Let's take an open cluster as an example as to how we can figure stuff out about stars and star clusters and then galaxies after that. The Pleiades, the Seven Sisters, is a common sight in the fall sky. And it's a beautiful constellation, a little star grouping. It figures in myths and legends, and it's, pardon me, has a beautiful aspect to it. It's almost like a micro little dipper in there. People look at the bright stars and usually they count about 6 of them. And then the stories are all about, well, where's number 7? Because you need 7 sisters or 7 brothers. But let's skip over that and just talk about science for a minute. So let's take the brightest one. It's got a name. It's called Alcyone. And a star is going to have a certain amount of energy output. And so I've got a figure here. So that shows the energy output in the up and down direction. So we have luminosity in that direction, and where that dot sits in the up and down direction puts it at about 1,000 times brighter than the sun. If you look at that right-hand side, hopefully you can read the numbers. 1 is in the middle, and then above it is 100, and above that's 10,000. And then below the 1 is a 0.01, and then a 0.0001. And those are in units of the sun. So 1.0 is the solar luminosity. The other axis, the left and right axis, is the star's temperature. And astronomers can also measure that with colors. So the B minus V color is on the bottom axis, and then actual temperatures in astronomers' units of Kelvin degrees are on the top axis. So that is a hot star, and it's a very, very bright star. Well, let's take the next few. So let's go to the next 5 and plot those there. They're not quite as bright as Alcyone, but they're still pretty hot, and they're still quite bright. And then, of course, we can go one by one for all the fainter stars that might be in the cluster, and we get a nice ordered picture that looks like this. That's pretty nifty. So the universe lines up for us in this particular luminosity temperature diagram. And we put some names on there. So we have a main sequence. And then what happens at the top of that main sequence is that some of those brightest ones have begun to leave the main sequence. They've begun to use up their hydrogen fuel, and they've begun to evolve away. And by evolving away, I mean they get brighter, and they're about to become something spectacular. They're about to become a red giant, which is huge, and then they will shortly end their lives after that and disappear forever. So their days are numbered, at least on astronomical timescales. Human timescales, okay, it takes a while. So main sequence here is the key word, and then that point where the stars leave the main sequence, that's called the main sequence turnoff. And that's a pretty important point because that lets us figure out an age, and I'm going to show you how to do that here in a minute. Another thing you do if you want to study galaxies, though, is these are just ordinary stars. And we can take spectra, and we can compute spectra, and we can make really solid guesses as to what the spectra of each of those stars is going to look like. And so we can add up the spectra if we wish, and we can make a model galaxy out of it. And then back to the main sequence for a minute. Those stars which are the brightest one, Alcyone and in the Pleiades, that's about 10 times more massive than the sun. A star like that doesn't live very long. It lives 30 million years. So that's barely longer than, my, what should I say? My old-fashioned detective's magnifying glass. But it's a long time for a human. It's a short time for a star. And then I marked a 5 solar mass star down there. That lives a lot longer, 180 million years. And then if you go to a fainter star, that lifetime is even longer and longer and longer until you get to something that's about the mass of the sun. And that has a lifetime of about 10 billion years. So our sun is, the clock is ticking. It's 4.5 billion years old, and it's only got 5.5 billion more to go. And then it's lights out for the sun. But you see the orderliness here, and you can see that a star cluster like the Pleiades is somewhere between 10 and 5 solar masses at that main sequence turnoff area, and it's age, therefore, is somewhere around 100 million years. So star clusters are really pretty cool. You just go to the bluest, brightest ones, and you can kind of read off of a graph like this how old that star cluster is, so you know when it formed. And in the case of the Pleiades, it formed during the Jurassic while the dinosaurs were walking around. So back to galaxies, let's draw this analogy. So a galaxy is made of star clusters. So here's a few star clusters, and I'm going to sort of mix them together and make a galaxy on the left. And then in my computer, I'm going to mix up the stars in the right proportions. And I'm going to make myself a model galaxy spectrum. So that's my grand business, and that's what I do. So the observer, which I do sometimes, is to look at a galaxy with a telescope, and the telescope is equipped with a spectrometer, and you get a spectrum from that galaxy. And then what I do is I take the theory of stellar evolution, I add all the stellar spectra together, I fold in something called the initial mass function, the IMF, to give me how many stars are there in each little phase, and I get myself a model spectrum. So I have an observed spectrum and I have a model spectrum, and then I can compare them, and then I can find out things. Things like, when did the stars in that galaxy form? How metal rich are they? Did the heavy elements build up quickly or slowly? And then maybe even advanced questions about merging, quenching of star formation, and accretion of new material, and maybe some connection between spirals and ellipticals and when the stars formed. Maybe there's interesting things to be learned from all that stuff. And here's a spectrum. Here's 3 spectra, but let me start with 1. So these are model spectra, and this is really what I do for a living. So it's kind of exciting for me to show it to you, and maybe intensely boring for you to look at it. But this top one, this top one is a fake galaxy that I cooked up in my computer, which is 5 billion years old and a little less metal rich than the sun. And then I do 2 things to it. I triple the age, and that gives us one of those lower spectra. So that removes some of the blue stars from the top of the HR diagram, makes them disappear so it looks redder and older. And then the other thing I could do is add more heavy elements to it. And so I add about a factor of 2 more, and that gets us the kind of the dotted one down there. And there's kind of an issue. So those 2 lower spectra, you can maybe not even see that they're different. They're on top of each other. It looks like 2 spectra that are merging into one. So this is interesting and irritating, because those 2 spectra look really similar, even though they're a factor of 3 different in age, and they're a factor of 2 different in metallicity. This is called the age metallicity degeneracy. And that means that it's kind of like a cosmic show where it's a mystery wrapped in an enigma, because you can't know either one. If you can't know the heavy element abundance, then you can't know the age. And if you don't know the age, you can't find out the heavy element abundance. And so you don't know either one. But like any good detective, you pound some pavement and you wear out some shoe leather, and you think of other ways that you might proceed. So let's go back to our first light detective, Joseph Fraunhofer, and what he was up to. So he was looking at different elements in the solar spectrum. Let's do the same in galaxy spectra. So here's another spectrum graph. This one's in the blue. And this shows you the influence of various elements. So if you add nitrogen to a spectrum, you'll get this signature there due to the CN molecule. And if you add calcium, you'll get a different signature. And if you add chromium, you get a complicated but still different signature at the end. And then on the bottom is kind of the sum of all of these different elemental absorptions that end up giving you the final answer there. So you can hopefully at least track ratios of elements together. And then I'm just about through with figures for you, and thank you for your patience. But let's look at this interesting 4-panel guy. The Fraunhofer features that are featured here, this H beta, that's Fraunhofer's F. And then this magnesium one is Fraunhofer's little b, lowercase b. And iron 5270 is E, letter E for Fraunhofer. And then there's besides those, so that's like measuring the strength of a couple of those absorption features. Well, the cool thing that happens in terms of the models, this is a complicated figure, but you see those numbers that say 2, 3, 4, 5, 8, 12, those are ages. So any galaxies that have those ages should lie near those lines, 2 billion years, 3 billion years, 5 billion years. And that's almost all that's on here. So there's an age sequence, and then the other dotted lines going left that are more vertical, those are metallicity features, so metallicity lines. And then there's one galaxy on here, and it's M32. So that's our little guy, our little companion of M31. In the middle of it is the dark bit that's a triangle, and then the outsides, going toward the outsides, are the cross symbols. And the nifty thing about looking at these spectral features is that you know by looking at this thing that the middle of M32 has a certain age. It's between 3 and 5 billion years. And then when you go to the outsides of the galaxy, it gets older until it's about 10 billion years old in the outsides of the galaxy. And in the 4 different panels here, it's always in a slightly different place. And so there is some uncertainty here. And part of that is real uncertainty, but part of it is that magnesium and iron and carbon are a little bit different than the solar mixture in this galaxy. So it does actually have an altered chemical abundance, which is really freaky and unexpected. And we don't know, we never expected that, actually. So that's quite an interesting thing. If you remove the H beta feature, it gets a little even clearer. You'd expect if the solar mixture was right, you'd expect these lines, these tilted lines, that would be the case. But then when you put the galaxies on it, they sort of ignore what your computer put out, and they do their own thing. And they do it in such a way that we got an iron feature and a magnesium feature, and it looks like magnesium is winning. Like the magnesium gets really strong for all these galaxy dots there. So in a figure like this, you interpret it with age going kind of that away in the diagram, and then the overall heavy element abundance should go back and forth that away. And then the galaxies don't do that. So the galaxies are screaming off to the right of that. And if they had more iron, magnesium, they'd go that way. And that's what they're doing. And if they had more iron, they'd go that way. And maybe M32 is doing that one a little bit. M32 is down. The asterisk on the far left is M32. So a diagram like this, we understand this in terms of showing us super clearly that big galaxies, at least the big elliptical galaxies, have more magnesium than the sun, and more magnesium than any of the stars around us in the Milky Way. And that gives us a new mystery. Why should that be? So here's the state of the matter here in year 2023. We can use diagrams like that to find ages for galaxies, crude ones, but useful ones. So we find out that elliptical galaxies are, without the spiral features, those guys tend to be quite ancient, whereas the spiral galaxies are always forming new stars, and they're simmering along just nicely with their roughly constant star formation. We also find this very interesting thing about heavy element abundances. So big E's, so big elliptical galaxies, don't have the solar ratios of these elements. They have more magnesium, they have more sodium, they have more carbon and nitrogen and oxygen, but they have about the same amount of iron, cobalt, nickel, and other heavy elements like that. We halfway understand this, and we halfway don't understand this. So here's a great mystery for the near future. So we can ask lots of questions at this point. You know, what does the mass of a galaxy matter? Does the galaxy assemble itself knowing it's going to have these altered elemental abundances, and what causes it? And we know kind of where heavy elements come from, so maybe that has something to do with it. So the origins of heavy elements come from 5 places. So if you can read the words here, Big Bang nucleosynthesis created hydrogen and helium mostly. And then the rest of this figure is an HR diagram, not an HR diagram, pardon me. The chemical periodic table of elements is what that is. Ah, I've got astronomy on the brain. Another place that you can manufacture, so Big Bang is kind of boring. Hydrogen and helium, that's pretty much it, and traces of lithium, beryllium, and boron. After that, it's up to the stars to manufacture the heavy elements that we need for our existence. And one source, the next source on here is in green, that's asymptotic giant branch stars. So those stars will manufacture an interesting mixture of elements, mostly carbon and nitrogen to start, but then they also have an interesting what they call a neutron capture process, in which you can build up some really heavy elements. So asymptotic giant branch stars are medium-sized stars, are going to be about 5 times the solar mass, and they will die quietly. They don't give us supernova or anything, but when they blow away their outer envelopes, those envelopes will be enriched with quite a bit of heavy stuff. By the way, each little sub panel on here, each little square, it's got this. They have these shark fins, kind of waves in them. That's supposed to be kind of a time graph of the buildup of heavy elements with time, color coded by source over the lifespan of the universe. So this is a lovely diagram to sort of pore over for at least half an hour, tracing all the origins of the elements. It comes from some models by Kobayashi. The other, the blue one, those are core collapse supernovae. Those are what you think of as a supernovae. So those are super big stars that blow up, and when they blow up, they have some element creation, and they're super common, and they pop off right away. So if you form stars, you're going to form some massive ones, and then they enrich right away. The red is a different flavor of supernovae. These are called type 1As, and they involve little white dwarf stars that merge or get matter stuck on them, and they explode as well. And then finally, if you have neutron stars that merge together, that can give you a few smatterings of elements as well. You see those in kind of pink here and there in the diagram. So this is kind of how things are supposed to go. So we can back out a little bit about galaxies by studying those origins. So it's a lot of supernovae and enrichment by other sources. And somehow that is different between galaxies of one type versus another. And before I close, let me just tell you what's next on my agenda. So we have more mysteries, and we would like to get better ages, for example. So my new push is to get a little better age information. So we'd like to really unravel the age question a little better. So to get back at that, let's go back to the Pleiades and the main sequence. And then if you look at the stars in the Pleiades, you notice it's got a couple of what they call Mercury manganese stars. So I've marked a section in blue here. Mercury manganese stars they have lots of these elements, mercury and manganese, and probably quite a few other super heavy elements. They're tremendously enriched. They're like 100 times or 1,000 times more if you just look at the spectrum. And so that means they look quite strange. If you look at the spectrum on them compared with a normal star here in black, a Mercury manganese star just looks pretty crazy in terms of its spectrum. So I got to thinking about these. These are called chemically peculiar stars, and they're not dominant in number, but there's about 10 to 20% of them. And that's a lot. And I was thinking, well, those spectral features, those are super strong. So maybe even if it's diluted by a factor of 5 or 10 from the total, maybe I can still detect those spectral features if the turnoff is in that area. And besides Mercury manganese stars, there are other flavors of chemically peculiar stars of about the same ratios. There's guys called helium strong stars, and then there's helium weak stars, Mercury manganese stars, and then they call it AM stars, metallic stars. And then finally there's if you reach about that 7,000 degree mark, this phenomenon stops. This is a surface phenomenon on the stars that does not cannot occur for stars that mix themselves up at the surface with convection. So it only works for hot stars. But when you line them up like this, you realize they're like they just line up 5 little segments there with different temperature. And if the turnoff is always moving from with age, it's going from the upper left and getting lower and lower, then over time you're going to have that main sequence turnoff cruise through each of these phases in turn. So you get 5 little signatures showing up if the stars are in those particular temperature bins. And so I'm chasing this down, seeing where this is going, and seeing if I could maybe, instead of one mean age for a galaxy, maybe I can parcel it up into bins, a whole history for the galaxy. And so preliminary results back to the Andromeda galaxy. That guy M110, I've decomposed it now. So with this new technique, I've discovered a 68 million year old parcel that's got quite a few. It's easy to spot, but it doesn't weigh very much. And then a huge mass formed about 1,850 million years ago, and that's quite precise, quite precise on the date there. And then there's another about half of the galaxy, which is really ancient, quite old, and I can't tell much about it. M31, the center of it anyway, is quite ancient and metal rich. So it's basically too old for this technique, so I didn't apply it there. And then M32 has got a fairly prominent 3,500 million year old population. And that's mixed up with something that's about 8,000 million years old. And so that's kind of where I'm at now. And I'm hoping to stretch this technique a little further because, of course, I'm a light detective. It's what I do.
Thank you, Dr. Worthey.
All right, I'm going to ask if there's anybody that has any questions from this audience. And I'm wondering if Calvin is kind of gone out the other side, and he may be monitoring the other side. Does anybody have any questions of anything? I'm sure that he would answer questions all different kinds. All right.
There you go.
A couple of the elements didn't have like beryllium and boron didn't have history attached to them. Why would that be?
Yeah, that's an interesting one. So boron and beryllium were created in the Big Bang, but in very small amounts. And what's happened to them is mostly destruction since then. And that particular author did not model this process. It's got a great name. It's this destruction process is called cosmic ray spallation. And so what happens is you've got a boron, and then cosmic rays, which are particles like maybe a proton, will come in and it will knock bits of it'll have like a micro nuclear reaction, and it will split apart the boron. So he didn't model this process, but basically we've been losing beryllium and boron ever since the Big Bang.
Okay, I love that periodic table. How many people remember the periodic table from their high school years? Yes, and it always fascinated me. And then when they came out with this is how all of this formed, I went, what? It wasn't something I really thought about, so it was great. You had a question? Yeah.
Why is it that clusters of stars, like globular clusters or the elliptical galaxies, why don't they collapse and just disappear or all get bunched up together?
Right. There is a minority of an elliptical galaxy that kind of does disappear. So most elliptical galaxies will have a black hole at the center, and that's basically a bunch of stars disappearing from the universe. Globular clusters don't, as far as we know, but they do have a process called core collapse. What happens for the older and kind of less agitated ones is they do get quite a concentration of stars there at the very center. But this takes a long time to happen, and it doesn't, those stars don't disappear. They're old, they're long-lived stars, and they will orbit this common center of mass basically forever. So it's actually quite a stable system.
Is there anyone else that has got any questions? Okay, now there'll be a test. In about 10 minutes. Okay, you had one question at the back? Yeah.
I wanted to ask, is the sun's temperature constant which would mean, like, are we totally to blame for climate change, or does the sun have something to do with it too? Does the temperature we get from the sun always stay the same?
Yeah, the solar temperature is very, very constant over a human lifetime. We have directly measured this, and we have also found out that the ultraviolet varies by, get ready, 0.1%, but it's a variability that's regular. It's like pulsating at that level. And the rest of it, not even 0.1%. It's really, really stable. Not over human lifetime. So over the sun's lifetime, when it was born, it was about 70% as bright as it is now. So back when it was born, it was 0.7. It's up to about 1 by definition right now. And then as it gets older, it's going to steadily get brighter. So, you know, set your calendar for 1 billion years from now, it's going to be a few percent brighter.
Well, thank you very much, Dr. Worthey. We really appreciate you taking time from your busy schedule to come and talk with us. And I know that it's not, you know, another time we'll actually get you here so that, you know, you can actually do it in person. So I'd like to have the audience kind of show their appreciation of Dr. Worthey. Thank you very much.
Thank you. Have a good night. It's a pleasure.
We're at about 9 o'clock. Yes, I just want to wait. It's probably.
Thank you, ladies and
Thank you, Mr. Worthey.
At 9 o'clock.
Hi, everyone. Welcome to What's Up in the Sky for August 26, 2023. Be sure to check out our gift shop in person or online. And we're grateful also for your memberships and donations, which help keep our educational programs running. And the proceeds from the gift shop do go to our educational programs. Note that we have summer daytime hours, and so stop by and say hi. We'll be doing dome tours and planetarium shows throughout the day when we're open. And the summer hours continue to September 29th, and they're Tuesday to Friday from 10 a.m. to 3 p.m. And note that we're not open on Saturdays in the daytime. And there is an admission price, which is necessary to raise money for our educational programs. And so for seniors, that's 65 and over, that's $12. Adults age 18 to 64 is $15. Students age 18 to 25 with valid student ID is $8. And also youth age 7 to 17 is $8. Children 6 and under are free. And it's also free to members of the Wasonic community as the observatory resides on their traditional territory. So let's talk a little bit about sunset, twilight, and sunrise. Sunset was at 8:07 p.m. Sunrise was at 6:22 a.m. And the sun was at its highest point at 1:15 p.m. at 52 degrees above the southern horizon. And there was 13 hours and 44 minutes of daylight. So that's almost 2.5 hours less daylight than at the summer solstice, where we had over 16 hours of daylight. So astronomical twilight ends at 10:04 p.m. and begins at 4:23 a.m. And so that means we're starting to have a lot of true darkness after 10 o'clock, and so that's great that we're starting to get that into the evening. So the moon phase is just past full, and it's still almost 80% illuminated, and it's what we call a waning gibbous phase. And however, I think combined with fire smoke, that means that the night sky will appear relatively bright, and it'd be difficult to see stars through the fire smoke. And moonrise was at 5:54 p.m. this evening. We'll talk a little bit more about that contrast effect in a second or two. And so what about the planets? So let's talk a little bit about the planets, and I'll put Stellarium up here. And so here's Stellarium, and you can see the time is set for about 8:30 in the evening. So Saturn rises sort of in the east at around 8:09 p.m. and will soon be well placed in the evening sky after sunset. And it's rapidly becoming the feature object of late August and soon early September. And it's a great target even for small telescopes. And Jupiter also rises in the east, rising just after 10:30, and I'm just going to bump the time to that. And there you can see it coming up, and the planet Uranus is also close to it in the sky, and you can see the names overlapping there. So how is the fire smoke affecting our offerings in what we can see? And as I said, the present fire smoke situation is making observing quite limited. We can't, for example, see many of the stars that you see up on the screen here due to the fire smoke, as the fire smoke absorbs light. And as I said, when combined with city lights and moonlight, it makes the sky look brighter and it reduces the contrast in the sky, and so it masks the stars quite effectively. On the other hand, if you're looking at the moon through a telescope, or Saturn or Jupiter, you'll notice that it might actually make them look less bright and reduces some of the glare that you see. And it potentially actually improves the image a little bit. So there's still a couple of things you can look at if you have a small telescope. And just as a little warning, of course, if you're actually looking at towards the sunset, you should never look directly at the sun, because even with the fire smoke, it's going to be harmful to your eyes. So don't think that just because the sun looks dimmer that it's safe to look at, even though it might look fairly dim and red. Okay, for summer constellations, we're not going to go into talking about those because you just really can't see much detail right now. But let's take a look at the bright star Capella over sort of in north-northeast. And when it's low like this, it'll appear to flash through the various colors of the visible spectrum, because we're looking through different cells of air turbulence in the sky. And so we could be looking through up to, say, 25 or 30 times as much air when we're looking at a star down this low as compared to when it's overhead. And so you're looking through that much more air turbulence with all of the prismatic effects of all of those little air cells. And so it might flash red and blue quite noticeably. And when I worked at the observatory back in the 1990s, I used to take calls from some people wondering what they were looking at. And some people thought it was a UFO or something, but I'd always check the time and where they were looking. And sure enough, it was likely just Capella visible in the sky. And we can actually get another great view of this kind of effect if we advance the clock to 5 a.m. So let's just bring this actually back from 5:30 to a little closer to 5 a.m. And you can see that we have Sirius over here and the planet Venus, and Sirius is the dog star, as many of you know. And we refer to the dog days of summer, as I said in an earlier feature, as being that time when you're first able to see Sirius in the morning skies. And so if you're further south, like in the southern US, you will actually have the dog days of summer occurring earlier because they would be able to see it earlier. But for us at this latitude of almost 49 degrees, it's not until late August. So just make sure that you don't confuse it with Venus, which is just a little bit further north on the horizon there. But one thing to compare is the amount of flashing between colors that Sirius has versus Venus. And Sirius is the brightest star in the nighttime sky, and it's also a point-like source. And so you'll see it flashing between fewer individual air cells, whereas Venus has a small but significant width to it, and it'll have more parallel bands of light that'll be sort of averaging out this flashing effect. And so you won't see the colors of the rainbow typically when you're looking at Venus at that kind of altitude above the horizon compared to a bright star like Sirius. But take a look at Venus if you can in morning twilight through a telescope, because you should notice that it looks like a crescent shape. It's only 7% illuminated tomorrow morning. And so that should be quite a sight and it'll soon begin to dominate the early morning skies. And note that you have to have a very clear eastern horizon to be able to see either of them on this date. So it's very sad for all kinds of reasons that we're still dealing with the fire smoke situation. But I do hope, as we always say here, that you keep looking up. And thanks for joining us this week, and we'll see you next time.